This Zoom session is being brought to you by the Fractal Picture of Itself. All right, let's see, we got through to P section P2 here. As I mentioned, homework P is available on the Canvas. Here it is. They're all written up. These should be equivalent to the homeworks available in the homework syllabus for edition 6. This may not be the same as edition 7. That's unfortunate. Anyhow, but here it is available to you, and I will be getting the next homeworks and so on available in as the chapters come up. Where are we?
And we should be able to find like example problems that are like really similar. Because I haven't even looked in my edition 7 yet because it was posted, but there's probably going to be stuff that's like the same if we need an example.
Yeah, and odd numbered problems with answers at the back of the book, and also, of course, as noted before, I work odd numbered problems here in the Zoom sessions and the modules. So let's proceed. We'll be doing P3 and P4. P3 is integer exponents in scientific notation. P4 is radicals and rational exponents. We proceed. Okay, P3, right. X to a power n. X is called the base, is n, the little thing on the top is n. Sometimes you use a caret, a kind of upside down V instead of this raised power thing. One of the biggest problems is people write x to the n, only they write n kind of right down next to it like it's x times n. Try to avoid that type of graphical error. Anyhow, x to the power n, you start with 1, then you multiply by x n times. So x to the first is just x. X to the second is x times x, also known as x squared, because if you have a square with a side of x, then the area is x times x. X to the third is x times x times x, called x cubed, because if you have a cube with a side of x, then the volume is x to the third power. X to the fourth power is x times x times x times x. I suppose if we continue with this geometric metaphor, we would call it x tesseracted, but tesseracts are strictly for science fiction. And we go on from there forever. Now, if we multiply powers of x, then the exponents add. So x to the second times x to the third. That's xx, that's x squared, times x to the third, xxx. That's 5 of them, x to the fifth, because 5 is 2 plus 3. In general, if you multiply powers of x, then it's the sum power. The power is to the sum. X to the a times x to the b is x to the power a plus b. Now here we have something slightly different. Instead of x squared times x cubed, it's x squared itself cubed. That's x squared times x squared times x squared. We add the exponents, x to the 2 plus 2 plus 2, that's x to the 6. And why 6? Well, 2 times 3. And in general, if you repeat an exponent, x to the a, that to the power b, you get a multiple for an exponent, x to the power ab. Here we have a power of a product, xy to the second, that's xy times xy. Rearranging a bit, you get xxyy, which is x to the second times x to the second. So it's as if this second power distributes over the multiplication. And in general, that happens in general. Xy to a power a is x to the a times y to the a. So exponents, powers, distribute over multiplication in much the same way that multiplication distributes over addition. And when we get to logarithms, we see that the analogy is exact. Here we have x over y to the second. So we're just taking a power of a ratio. And also that's x over y times x over y. That's xx over y, x to the second over y to the second. So here the second power distributes over a ratio. X over y to the a is x to the a over y to the a. So yeah, power distributes over ratios in much the same way that multiplication distributes over subtraction. And again, when we get to logarithms, we'll see that that analogy is exact. Now, if you look at a power of n, you can pull out a 1, and it'll be x to the n minus 1 times x. So if you divide out x to the n, divide by x to the n minus 1. So to make a 1 less power, you divide by x. Now, if we extrapolate that to 0 and negative powers, we get definitions for 0th powers. X to the 0 is x to the 1 minus 1. So that's x to the 1 over x, which comes out to 1. The 0th power equals 1. Now you can see that when we go back to our original definition. X to the n, you start with 1 and then multiply by x n times. If n is 0, just add, you have x to the 0 just will equal 1, and no multiplications at all, so it's 1. X to the 0 is 1. X to the negative 1, that's x to the 0 minus 1. X to the 0 over x, that's 1 over x. So negative 1 power is a reciprocal. Negative 2 power, x to the negative 1 minus 1 is x to the negative 1 over x, which it works out to 1 over x to the second. So x to the negative n is 1 over x to the nth. So a negative power is a reciprocal. A 0 power is always 1. We use this to supplement this definition here. This is for positive integer exponents. This is for 0 and negative powers. It follows, for example, that since a negative nth power is 1 over an nth power, it follows that 1 over a negative power is an nth power. So they're reciprocals of each other. And if you take a ratio of negative powers, well, x to the negative n winds up in the denominator, and y to the negative n winds up in the numerator. So these switch positions while the powers change sign. Now, if we had x to a second power divided by x to the fifth, well, that'd be xx over 5x's. 2 of them cancel, leaving 1 over 3x's. 1 over x to the third. It's x to the negative 3. We can get a negative 3 by subtracting 2 minus 5. So x to the 2 over x to the 5 is x to the 2 minus 5. If you add x to the second over x to the second, that's just 1 over x to the 0, which is x to the 2 minus 2. Again, we're subtracting powers. And if x to the fifth over x to the second, that's 5x's over 2x's. 3 remain, that's x to the third, and the third is 5 minus 2. So in general, if you have a ratio of powers, you can take the difference, a ratio of powers, and you can take the difference of the exponents. Just like when we have a product of powers, you add the exponents. Now let me see, let's jump forward a bit, shall we? So for example, x to the fifth times 5 is what? Well, x to the fifth times 5 to the third times, 5 to the 1, that's 5 to the 3 plus 1. That's 5 to the fourth power, which comes out to 625. Oh, by the way, if you look at this, I must confess that it's a little bit too easy to confuse 5 to the fourth power to 54, and they are very, very different things. Here's 3 to the second times 3 to the 0. That's 3 to the second, because 0 adds to 2 plus 0 is 2. Or 9. X to the second cubed. That's x to the 2 times 3. That's 2 to the 6th. That's 64. Here we have 2 to the 8th to the 0, negative 5 to the 0, and the opposite of 5 to the 0. Watch out, there's trickiness here. These two, they're both 1. Here, the general rule is that an exponent binds tighter than a minus. So this will be opposite of 5 to the 0 or minus 1. Please note the difference between these two. For this one, we do the negative first, then a 0 power, getting 1. Here we do a 0 power first, and a negative, getting negative 1. Here we have a to the 9th, a to the negative 2 over a. What's that? Well, we write this denominator as a to the first. I always recommend, you should always be careful about that. Just because there's nothing here doesn't mean it's a to the 0. It's a to the first. A to the 9 plus a to the negative 2 over a to the 1. You will subtract the 1. A to the 9 plus negative 2 minus 1 is a to a 6th power. It's a to the second, a to the fourth, all cubed. What's that? Well, the thing inside is a to the 2 plus 4, that cubed. Is a to the 6th, that cubed. A power of a power is a multiple power, a to the 6 times 3, or a to the 18th. Here we have 2 to the second, 2x to the second times 5x to the 6th. What's that? Okay, first thing we do is to distribute the second power over the 2 and the x. 2 to the second, x to the second times 5x to the 6th. Okay, 2 to the second is 4. Here's a 5. X to the second times x to the 6 is x to the 2 plus 6. So 4 plus 5, that's 20. 2 plus 6 is 8. Result is 20x to the 8th. Now here we have some gnarly stuff. 5x to the negative second squared times z cubed. And here we have a real mess. 3a to the fourth b to the negative 2 cubed. A to the second b to the negative 1. What's that? Okay. We'll start with a. Okay, here for this one, first we distribute the second power with a 5 and the z to the negative 2. So 5 to the second times z to the negative 2 second times z to the third. 5 to the second, well, that's 25. Z to the negative 2 to the second, let's see, multiply these and get z to the negative 4th. So 25z to the negative 4 of z cubed, add the negative 4 plus 3 here, and you get 25z to the negative 1, aka 25 over z. Now here, this one, oh, this is a mess. 3a to the 4th b to the negative 2 cubed times a squared b to the negative 1 is what? First thing we do is we distribute the third power over each of these factors. 3 to the third, a to the 4th to the third, this is b to the negative 2 to the third times a to the second, b to the negative 1. For these, we multiply exponents. A to the 4 times 3 is a to the 12. B to the negative 2 times 3 is b to the negative 6. And 3 cubed is 27. So 27, a to the 12th, b to the negative 6, a to the second, b to the negative 1. The powers of a we add up, 12 plus 2. The powers of b we add up, negative 6 plus negative 1. And so get 27, a to the 14th, b to the negative 7th. And we can write that with the positive exponents by writing b to the negative 7th as 1 over b to the 7th. So 27, a to the 14th, all over b to the 7th. You know, here these other problems involve scientific notation. Let's get to that. Scientific notation. Called that because physicists, chemists, astronomers, and so on use it because it's very useful for denoting very large and very big numbers, which happen a lot in physics, chemistry, astronomy, etc. It's of this form: n times 10 to the p. N is a number between 1 and 10, at least 1 less than 10, and 10 to a p. P is a whole number, an integer, called the magnitude. So for example, here's 3.22 times 10 to the negative third. That's in scientific notation. This negative third, it means it's a small number, so we move the decimal point left 1, 2, 3 spots to get 0.0032. These are equal. Here's 3.2 times 10 to the third. Well, that's this 10 to the third means this positive power means it's a big number. So we move the decimal point to the right 3 spaces, got 3,200. Here's 137,000. Okay, first the number in front, 1.37. What you do is you take the top of the number and put a decimal point just to the right of the leading digit. 1.37, and it's 1, 2, 3, 4, 5 zeros, powers of 10, so it's 1.37 times 10 to the 5th. You have 0.00137. Again, we have a 1.37 part, and then to move the decimal point to the right of the 1, we have to move this decimal point 1, 2, 3 spaces to the right, therefore times 10 to the negative third. All right. Now these, this 10 to the p is called the magnitude or order of magnitude. So for a number between 10 to 99, those are in the tens. 10 to the first. For 100 and 999, that's something in the hundreds, 10 to the second. From 1,000 to 9999 is in the thousands. For things in the power 10 to the fourth, that number is 10 to the fourth. And that number is a name. It's a good name. I like it. It should be revived. Myriad. I like that number. A myriad. It's 10,000. Or here, 100,000s. Those I also have a name. They're called multitudes. These are old names. You can find them in the Bible. And I think they're useful. I think it's a big shame that there's a gap in names between thousands and names, and these fill the gap. A multitude is 10 to the 5th. 10 to the 6th is in the millions. 10 to the 9th is billions. 10 to the 12th is trillions. These are useful because, again, it's a gap that comes in. Around just before the Second Gulf War, there was lots of demonstrations in the streets, and the day after, the SF Chronicle said thousands marched. That really annoyed me because I was there and I knew it was a lot more than mere thousands. It would have made more sense just as headlines to say myriads march or multitudes march. It would have alliteration, but they decided to step on the story and put it on page A7. I canceled my subscription to the Chronicle. Anyhow. Now, scientific notation is useful for writing very large or very small numbers because in science you get those numbers a lot. So, and it's a way of to avoid the danger of writing too few or too many zeros, which would be a serious error. So you have 0.0000000203. Well, okay, you put the decimal point just to the right of the 2.03. How far do you have to move the decimal point? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2.03 times 10 to the negative 9. Here you have this monster, 50160. Oh my goodness. Okay, before we move the decimal point just to the right of the leading digit, 5.016, like here. And how far do we have to move that decimal point? 3, 6, 9, 12, 15, 16. So this is 5.016 times 10 to the power 16. Now, sometimes you get something that is not quite in scientific notation. 23.65 times 10 to the 6th. This is not quite right. It's not between 1 and 10. So we rewrite this by moving the decimal point over a spot, 2.365 times 10 to the 1st. That's what this is. And that times 10 to the 6th gives you a 10 to the 7th. 2.365 times 10 to the power 7. Here's a 0.0317 times 10 to the negative 2. We have to move the decimal point just to the right of the leading digit to get 3.17. We had to move that point 2 spots to the left, to the right, excuse me. So that's 3.17 times 10 to the negative 2 times this 10 to the negative 2 gives you a 10 to the negative 4. 3.17 times 10 to the negative 4. One of the virtues of scientific notation is for multiplying and dividing very large and very small numbers, because the powers of 10 are easy to multiply and divide. You add and subtract the exponents. 1.3 times 10 to the 4th times 7.8 times 10 to the 5th is what? You multiply these two parts together. 1.3 times 10, 7.8 is 10.4. You add the exponents. 4 plus 5 is 9. 10.14 times 10 to the 9th. But this is not quite in scientific notation because this is not between 1 and 10. We write this 10.14 as 1.014 times 10 to the 1st. That multiply with this, you add the exponents, you get 1.014 times 10 to the 10th. So that's this multiplication. Now here we divide. 2.686 times 10 to the 10th over 7.9 times 10 to the negative 7. Okay, we divide these parts, 2.686 over 7.9. We subtract these exponents, 10 minus negative 7. This part's easy, that's 10 to the 17th. This part, you run to your calculator, got about 0.34. Ah yes, significant figures. These had 4 significant figures, this had 2. It's generally good form to use the lowest significant number of significant figures, because that's really all the accuracy you really have. So this comes out from the calculator as 0.34, and that times 10 to the 17th. Again, this is not quite in the right form. We write it as 3.4 times 10 to the negative 1, and that times 10 to the 17th is 3.4 times 10 to the 16th. All right, we did these examples. Here we go. Write this in scientific notation, 69,300,000. Well, move the decimal point here to 6.93 and has to go 3, 6, 7 spaces. So 6.93 times 10 to the 7th. Here we have, here's a real monster. Well, okay, 7.2 times 10 to the 3, 6, 9, 12. 7.2 times 10 to the 12th, 7.2 trillion. 0.0000028536. Write this as 2.8536. We move the point 1, 2, 3, 4, 5 to the right. So 2.8536 times 10 to the negative 5. Here is 0.001213. Okay, this we write as 1.213. We move the decimal point 1, 2, 3, 4 to the right. So 1.213 times 10 to the negative 4. Okay, here we have a mess. 1.295643 times 10 to the 9th over 3.610 times 10 to the negative 17th times 2.511 times 10 to the 6th. Whew, what is that? Okay, here we go. Okay, these parts we put out in front here, 1.2956743 over 3.610 times 2 to the 0.511 times 10 to the powers. You have a 9 here, minus this negative 17 here, minus this 6 here. Okay, this part's easy, it's 10 to the 20th. This part comes out to 0.1429. There's only 4 decimal places justified because these have 4 significant figures and these has more, but you can't use the more significant figures because these are less accurate. Now I'll rewrite this as 1.429 times 10 to the 1, negative 1, times 10 to the 20th. So you add these up and get 1.429 times 10 to the 19th. Here's a cute one. Now this is why I talk about why scientific notation is good for using astronomically large numbers, because astronomy has large numbers. 1 light year is, oh dear, I should have said 5 million trillion miles. Okay, this is page 11, 5.9 times 10 to the 12 miles. Okay, that's my mistake. I shall be changing this in the canvas after we're done. Okay, so 5.9 trillion miles per light year, and Proxima Centauri is 4.3 light years away. How many miles is that? Okay, take 4.3 light years times, and with this over light year, 5.9 times 10 to the 12 miles per light year. Well, these are equal, so this is equal to 1. It's a unit. It's called a unit conversion factor. I multiply light years by this because this way light years cancel out, and we're left with the units of miles, which this times this works out after a bit of work to 2.5 times 10 to the 13th miles, 25 trillion miles away. And that's the closest star. Okay, that's it for this one. Let's stop here, stop recording.